Hello everyone, thank you for logging in and watching this video tonight. I hope it's not too late as you are working through this homework for tomorrow, but I'm excited for you guys to learn some new material. So as you know, we've been working a lot with quadratic equations. As you can tell, we are going to spend a little more time with them, but I know that you guys are becoming masters at the material as you guys are understanding different methods of solving. Remember, we've worked through factoring, we've worked with graphing, we've worked with completing the square, which I know you all were a huge fan of, as well as using the quadratic formula. And remember how we derived the discriminant from that. And so you guys have a very good understanding of how to solve quadratic equations and implement them into finding answers from your worksheets. However, you may be wondering and asking yourself a bigger question as to why we need to know quadratic equations. I mean, how often do you come across them in the world around you, and where do you see them? But lucky for you, quadratic equations are found in many places. So we're going to take a look at just some places you may find quadratic equations and where you might not expect them to have used quadratic equations. So our first example is the St. Louis Arch. As you can tell, we have a very good parabola shape here. It's downward facing, and we have our vertex up top. As you know, our axis of symmetry will run right through the middle. And our solutions will be where the ends are meeting the ground. So architects, as they were constructing this arch, had to really take in consideration the quadratic equation that would be used to determine the heights and the widths and lengths of all the materials that they needed to use while making it. So even a really cool fancy design architectural piece uses quadratic equations. Another example would be the aqueducts that Rome used to carry water. And it's very neat to see how even ancient history used quadratic equations and parabolas to help implement a very efficient water design as well as just visual effect. Another place you can find them, however I don't know if they use them, is the McDonald's arch. As you can see, we have a narrower parabola here. It's still downward facing, and our vertex is up top in these arches, and our axis of symmetry will fall on the lines. Another place you can find quadratic equations is with any projectile that will be going up into the air and then coming back down. They take a quadratic effect most of the time, depending on how you're shooting and launching your materials. So as this guy is shooting the basketball, it's going to go up, it's going to reach its vertex right around here, and then come back down through the basketball hoop, hopefully. However, we know that does not always happen. So quadratic equations are all around us, but more important than to just noticing them is to how we are going to be able to create them. So that's what we're going to work on now, is how we can construct a quadratic equation. So as you know, we've been working with the standard form of a quadratic equation, which is y equals ax squared plus bx plus c. And you guys have had a lot of time working through that and working with that formula. But now we're going to take a different approach, and we're going to use the vertex form. So the vertex form of a quadratic equation looks like this. We have our y equals a. Remember, we had a in our first one. Then x minus h, which is squared, plus k. Now, h and k are new to us, and they are the vertex. So they're still an xy coordinate pair. However, they're just a special xy coordinate pair, which is our h and x. And hopefully this will make a little more sense as we look at an example. So we are given this graph for points A, B, and C. And from here, we're going to have to be able to identify our vertex and then also identify another point on this graph. And then we will plug those values into here. So our points are A, which is our origin, is our 0, 0, B is 1, 1, and C is negative 1, 1. Now A is also special, as in it is our vertex. We can tell here, because there are the points on the opposite side up top, that we know this parabola should be facing upward and will be here on our graphs. So from there, we're able to identify our vertex, which h will be 0 and k will be 0. So now our next step is to plug these into our equation. From here, since we know these values, we can get this equation. And as of right now, yes, it looks kind of messy, and it will at the beginning. But then our next job is to simplify this equation. So we know that since y is 1, we're plugging in 1. And we're solving for a. And then since x is 1, plug in here. H is 0 and k is 0. So when you're using vertex form and that you're given 2 points, with one being the vertex and another on the graph, you should always be able to fill in every position other than a. And so you should solve for a for your first step. So now we can simplify this down. When 1 minus 0 is 1, squared is still 1. You can get rid of the 0. And now you know that a equals 1. So our final equation, when we plug back our values in to here, we get y equals x squared. Now, you may be asking, well, where's h and k? Well, for this situation, since h and k are 0, they will disappear. And since 1 is our a value, we can also not have to write it. So we actually get the very normal quadratic equation, which is y equals x squared. And now you may be wondering, well, how do I know for sure if that's our equation? Well, lucky for you, we have this app called GeoGebra, and I encourage you guys to use it as you may, and you can click start graphing, but I have already used it to plug in our points. And to check this, we can just type in y equals x, and then you can click down here and you get an x squared, and as you can see, it runs right through all of our points. So we checked our work and we know that we do have the correct quadratic equation. Now let's continue on from here. We'll try another example where we have a different kind of looking parabola, which our vertex will be above our points. So here, where you can identify our vertex, which is B, which is at 4 and 5. And then we also just need to identify another point on our graph. So for this, we'll use A, which is at 0, 3. So our next step, as we used before, is to plug in these values into our equation. So we get 3 here for our y value, and we get our a, as we're solving for a. We have 0 for our x value of a, 4 is h, and 5 is k. So now we're going to solve for a, and if we simplify it down, you get negative 4 squared. This just turns into 16. You subtract 5 from both sides, you get a negative 2 equals 16a, and you're left with a equals negative 1/8. And so remember, you're not done when you get to a. You need to make sure you enter into your final equation, which for us turns into this. You have our y equals our a value, which we have to plug in, x minus h, which again is 4, plus 5 for k. And again, I encourage you guys to use GeoGebra to check your work whenever you are working with constructing an equation. So now you may be wondering, well, let's see, we know how to construct an equation when we're given 2 points, but what may those 2 points represent, and how is that going to be beneficial to us in the future? So we're going to work through now a real-world example problem that is also on your worksheet, so please follow along, and if for any time you guys might need to stop and rewatch a part, I encourage you guys to do so to make sure you guys are fully understanding how we are going to be constructing this equation to go through our points, because it is beneficial to know when you guys are going to be doing that and how to do it for tomorrow's activity and for later on in life for many, many situations. So we have to throw a ball straight up in the air and catch it at the same height you released it. So we know if we're going to start at 2, it's going to catch it again at 2. This is you just tossing it and catching it. So the parabola at right shows the height y of the ball in feet after x seconds. So we need to find what the equation of this parabola is. So in our sheet, we know our steps. Our first step is to identify our vertex. So as you can tell, we're going to have a parabola that's facing downward. So our vertex should be at the highest point, which here is B, and that's at 2, 4. Our next step is to identify another point on our graph, which we have is A, which is at 0, 2. And this, remember, is the initial position of where you have the ball. This is you holding the ball before you're even going to throw it. So now we can use these 2 points to plug into our equation. We have our y value here for 2. We're going to solve for a. We have 0 here for x, minus 2 for our h, and we have a plus a 4 here for our k. Now, remember, we can simplify this down, and we'll get a as negative 1/2. Remember, this is not your last step. You've done a lot of work up to here so far, but A is only you're only part way. You need to remember to make sure you go back and plug it into your original equation to get y equals -1/2, then the x minus 2 squared plus 4. So we have our a value, we have our h, and our k all plugged into our equation. So now that we are able to use our equations and we know that we can use 2 points to identify our graph, you guys are well equipped for tomorrow, where you guys will be launching a projectile, which I'm going to leave that to tell you guys tomorrow in class, while also being able to construct your equation, and then you guys will be tested on how well your equation works, and you'll be given an accuracy test. However, before you guys are ready for that tomorrow, there's this really awesome website that allows you to work with our quadratic equation, and I really want you guys to become familiar with the different parts. Now, the first thing you may notice about this is that we are back to using our standard form of our equation. This is to help you guys remember to identify what your quadratic equation should look like and the different aspects of it as you are using your quadratic equation, because we are able to simplify our vertex form into standard form, but we'll work on that in our next lesson. So, as you guys know, we have our a value. So our a value is going to determine our scale factor of what our quadratic equation will look like. As you can tell, we have a. It's just a simple, basic quadratic equation. This is actually the equation we found in our first example, is just y equals x squared. Now, I want you guys to think about what might happen if we make this negative. So if you need to pause this and think about it a little bit, I encourage you guys to do so. And whenever you're ready, just click play and we can find out. So you guys had a moment to take a look at, see what a might do if it's negative. So we'll plug in a negative. As you can tell, it flips our graph. So we know that when a is negative, our graph should be facing downward. This is a key aspect of understanding how your vertex form should look. If we go back and look at our examples, we can see that here we found a to be positive and our parabola is facing upward, and here we found a to be negative and our parabola is facing downward. This will be true of all situations. So tomorrow when you guys are working through your equation, if you guys are creating a positive a, I want you guys to think about what that might mean for your example. If you have an a that is positive, that means that you'll be starting at some point high up, dropping down, and then continuing up into infinity or whatever. And think about if that makes sense for your situation you are in. You guys should be starting at a point, then you'll be launching your projectile up into the air, and it'll be landing back down. So your a should become negative tomorrow, as in because we have gravity to blame as for the reason to go back down. Now that we've worked with a, let's see what happens if we make a bigger. What happens if this becomes 3? Look at how it shrinks our graph. So the larger a is, the skinnier your graph should become. If we were to make a only 0.1, look at how wide this graph becomes. So now let's go back and look at, if we leave a to just be our regular 1 for a normal quadratic equation, what happens when we apply a change in b? So let's make b 2. Look at how it shifted our graph, and that we know that our y-intercept is still 0, so it moved our graph downward, but it shifted our graph to the left. And this we can hear, this also allows you to see what the original equation would look like if everything were to just be, if you were just to apply the ax squared. So you can tell how it shifted. Let's see if we go a -2. Look at how it moves it to the right of the y-axis. Now also, we can look at it, if we just leave this as a 1, we will leave a little bit as a change. What happens if we make this becomes a 3? Look at how it shifted our graph upward, because c represents our y-intercept. Because remember, if x is 0, these terms will both be gone, and it will just leave you with c. So our term becomes up here. And you can also see with our original, where if you only applied c, it'll be somewhere along this line. So this tool is a really awesome site for you guys to use. I encourage you guys to use it, and it was also on your worksheet, so you guys can plug it in and mess around with this a little bit later tonight. I hope you guys got something good from this lesson and you guys are ready to come to class prepared and excited about our experiment that we'll be running tomorrow. Also, if you guys have any questions about any certain parts, feel free to contact me. You guys have my email, as well as take as many times as you need to rewatch this video as you can. I hope to see you guys all tomorrow, and thanks so much for listening in.